Hello, this is the lecture on refraction of light and other waves. Here we see a few images that show us refraction. So to get started, light travels in straight lines as long as it's in a medium that's uniform. So it can only bend when it reflects off of a boundary or it enters a new medium. And when it enters that new medium, it will bend, and we call that refraction. So that's our definition of refraction. Refraction is the bending of a wave as it passes at an angle from one medium to another. The reason refraction occurs is because the wave speed or wave velocity changes. Here's an analogy for why we'll get the bending when we enter a new medium as we change speed. And the analogy involves a lawnmower. Here we have a lawnmower on a sidewalk, and here's some grass. If we send this lawnmower in at an angle, this red wheel is going to hit the grass before the white wheel, and the red wheel will slow down. Since the red wheel is in the grass and is slowed down, but the white wheel is still on the sidewalk and still traveling faster, that causes our lawnmower to rotate a little bit as our wheels are moving at different speeds. And thus our lawnmower will change direction. It bends a little bit. This analogy can be used to tell us about how light bends as well. If our light ray enters a medium where it slows down, it's going to bend away from the interface and towards basically closer to the middle. We're going to call that the normal. And we'll define that a little bit later. Notice that the wavefronts also bend, as the wavefronts are also always perpendicular to the ray, the direction of motion of our wave. And it's just caused by that change in speed. Okay, so here are some terms that we need to know. Whenever we're doing optics, we will always measure angles with respect to a line that is perpendicular to the interface. We call that line the normal. Normal because normal means perpendicular, just like the normal force is always perpendicular to a surface. So here's our normal line right here. Those dotted lines are our two normals. The angle that the incident ray makes with the normal is called the angle of incidence. Usually we'll call it theta 1 when we're talking about refraction. Here's our theta 1. And the angle of the transmitted ray is called the angle of refraction. So this is our angle of refraction, theta 2. The amount that the light bends depends on the angle which the light ray strikes the new medium. And it depends on how much the wave speeds up or slows down when it enters that new medium. So it depends on both the speeds and the angle of our light ray. So we're going to define a new quantity called the index of refraction. The variable for our index of refraction is lowercase n. And the index of refraction is a dimensionless ratio of the speed of light in vacuum to the speed of light in that medium. So here's our true definition here. N is defined as c, speed of light in vacuum, over v, which is just our speed of light in that medium. Speed in whatever medium. Poor handwriting, but there it is. And c, our speed of light in vacuum, remember, is 3.00 times 10 to the 8 meters per second, to 3 sig figs. So that means the index of refraction for our vacuum is 1, because it's going to be c over c. And as when light enters these new media, it's always going to slow down, because nothing can go faster than the speed of light in a vacuum. So since we're decreasing this denominator, v, the index of refraction is always going to be greater than 1 for other materials. It's an inverse relationship between index of refraction and speed. So higher speed means a lower index of refraction. Slower light in that medium is a higher index of refraction. So here's an example problem. A light wave travels at 1.24 times 10 to the 8 meters per second in an unspecified transparent material. Find the index of refraction of the material. Well, we're given the speed of the light in that material, and we want to find the index of refraction, n. We know that n equals c over v. So all we have to do is plug in c and v. We know that c is 3 times 10 to the 8 meters per second, and we know that v is equal to 1.24 times 10 to the 8 meters per second. Meters per second cancels. Even r times 10 to the 8 cancels. So our answer is just 3 over 1.24. Plug it into a calculator. And we get an index of refraction of 2.42. Here are a couple of common indices of refraction. Obviously for vacuum, by definition, the index of refraction is 1 since the speed is c. But another important thing to note is the index of refraction for air is 1.00029. But it's equal to 1 to 4 sig figs. So when light is traveling through air, it's basically traveling at the same as the speed of light in vacuum. And we're going to know that the index of refraction is just 1. Water is about 1.33, glasses are about 1.5, and diamonds about 2.5. Higher index materials are said to be more optically dense than lower index materials. So if you hear something about light entering a denser medium, that means it's going to be going into a higher index medium like diamond, and it's going to be slowing down. So light would slow down in a denser medium, more optically dense medium. And here's a practice. Find the speed of light in diamond. Well, we know n equals c over v. If we solve that for v, we get v equals c over n. So that's just going to be 3.00 times 10 to the 8 meters per second over 2.419. We plug that in. V is equal to, plug it into a calculator, 3 times 10 to the 8 over 2.419. We get 1.24 times 10 to the 8 meters per second. Pretty close to what we found in the previous problem. So that may have been diamond that we were working with. This is Snell's law, and it's the mathematical law that governs reflection. It relates the two indices of refraction, n1 and n2, to the two angles of incidence and refraction, theta 1 and theta 2. Our full equation is n1 sine theta 1 equals n2 sine theta 2, where n1 is the index of refraction corresponding with the angle of incidence inside of that same medium, and n2 is the index of refraction for this for the ray that corresponds to theta 2. It doesn't really matter which one you choose to be 1 and 2, just as long as you're consistent with your numbering. So here are the three possible scenarios for when a ray of light, or really a wave, enters a new medium. Either, well, if the indices are the same, if n1 equals n2, then the speed of the wave does not change when it enters a new medium, so there's going to be no bending. If n2 is greater than n1, then that means n2 is going to be slower. And using the lawnmower method, we can see if it's slower, it's always going to bend towards the normal. So if it goes to a high index medium, it bends towards the normal. And if n2 is less than n1, that means it's moving faster in n2, speeds up. And using that lawnmower method again, we can see that it's going to bend away from the normal, always when it enters a lower index medium. These are the only three possible scenarios. Here's an example here. If you're looking at an object that's submerged in water, you're seeing light coming from it. But when light leaves the water, it bends away from the normal because it speeds up. You can see it bending away from the normal here. So we see light that is bent away from the normal, but we perceive light to travel in straight lines. So the image of the object is actually going to be above where the actual object is. We'll perceive it to be less deep than it actually is. So we'll have to look a little bit past it, a little bit above it, in order to see it. And this is really important if you drive in Houston. There's a lot of potholes and it rains. This means that anytime you're looking in the water, it's always going to be deeper than it looks because the light always bends away from the normal when it leaves the water. So if you see a pothole filled with water, avoid it. It's always going to be deeper and therefore more dangerous for your car's suspension than it looks. The atmosphere is a higher index medium than vacuum, so when light travels from the sun into the Earth's atmosphere, it actually bends towards the normal. So it's going to curve in towards the Earth. And what that means is we can actually see the sun after it's already gone past the horizon. This is an image of the sun, but it's actually behind the horizon. We're just seeing an image of the sun that appears to be above the horizon because of the way that light bends. Mirages are another example of this. If there's a temperature gradient, that is a temperature difference between the air low to the ground and the air higher up. In this case, if the ground is hotter, then it causes light from objects to bend upwards. So when we're looking at a distant object, we might, or light coming from it might bend down and then bend back up to our eyes. So we see an image of it down low on the ground. So when we see something like a mirage on the road, like right here, it looks like a reflection, it looks like water because we're actually seeing an image of something high up in the air. We're seeing an image of, in this case, just the sky that gets bent up into our eye. The Falstad ripple tank has a nice illustration of this if you go to the temperature gradient example. We could also have a superior mirage if cool air is low to the ground and the warm air is higher up. That's going to cause our light to bend downward. And so we'll see an image of the object above where the object actually is. This is a mirage, and it's a mirage of the boat above the actual boat itself. We see a nice clean image. And that's going to require the warm air to be up high. So we write Snell's law as n1 sine theta 1 equals n2 sine theta 2, and we know that n equals c over v. We can actually combine them. If we rewrite Snell's law as n1 over n2 equals sine theta 2 over sine theta 1, we can substitute in n equals c over v to both sides, and we get n1 over n2 equals cv2 over cv1. And if we combine that with our equation up here, then we get this full equation that relates index of refraction to wave speed to theta 1 and theta 2, our angle of incidence and angle of refraction. So this kind of combines everything, and this is how the IB writes the Snell's law and wave speed and index equation. So this allows you to relate indexes or indices to speeds, indices to angles, or speeds to angles. Let's do an example. A beam of what? A beam of light. A beam of light in crown glass, n equals 1.52, is incident on water, n equals 1.33. If the angle of refraction in the water is 40 degrees, find the angle that the light strikes the boundary between the glass and the water. Find the angle that the light strikes the boundary between the glass and water. Okay, so we always want to start with a sketch. We have two substances here. One of them is water, one of them is glass. So I'm going to draw these little kind of tick marks on the higher index substance. So this is going to be my glass. This is water. And we start with our beam of light in the glass, and it enters into the water. It tells us the angle of refraction in the water. So I'm going to just sketch out a normal here. The angle of refraction in the water is 40 degrees, so it's going to be something like this. 40 degrees, theta 2. Find the angle that the light strikes the boundary between the glass and water. So that's the angle of incidence. So I'm going to sketch out my normal for the glass. Since glass is n equals 1.52 and water is n equals 1.33, it's entering into a lower index medium. It's speeding up, which means it bends away from the normal. So my incident angle is going to be a smaller angle, theta 1. Theta 1. And I'm just going to use Snell's law to solve it. N1 sine theta 1 equals N2 sine theta 2. I'm solving for theta 1, so I'm going to divide both sides by N1. I get sine of theta 1 equals N2 sine theta 2 over N1. Now I'm just going to plug in my numbers now. N2 is, well, I said water was theta 2, so that's also going to be N2. Let me label it on here. 1.33 times sine of, what's my angle, 40 degrees, divided by N1, 1.52. And I plug that in, I get sine of theta 1 equals, calculator it out, since I'm using degrees, make sure I'm in degree mode, 1.33 over 1.52 times sine of 40 gives me 0.562. Now, we can't just divide out by sine. If we want to, if we want to solve for the angle here, we have to take the inverse sine. So we're going to get theta 1 equals the inverse sine minus 1, of 0.562. So I'm going to do inverse sine on my calculator. That's second sine. Inverse sine of 0.562 gives me my angle of incidence, 34.2 degrees. That's my angle of incidence in the glass. It is a smaller angle than 40, so we are good. Next, a ray of light travels through 3 transparent media. Rank the indices of refraction of the 3 media. So let's look at 1 and 2. From 1 to 2, it bends, well, it bends towards the normal. If it bends towards the normal, that means it is slowing down, so it's a higher index. So if we call this N1 and then N2, it's entering a higher index medium, so N2 is greater than N1. It's supposed to be a greater than symbol. When it goes from 2 to 3, it bends away from the normal. That means it is speeding up. That's a lower index medium, so N3 is a lower index medium than N2. Now we need to just compare N3 and N1. Well, if we look at N1, it's at some angle, and when it gets to N, well, if N3 were the same as N1, then this ray would be parallel to this ray. But they're not. The ray in 3 is further away from the normal. If it's further away from the normal, that means it has to be moving faster in that medium, which means it has to be the lowest index. So the lowest index is N3, and then the next highest is going to be, well, N1, and then the next highest is going to be N2. The more close to the normal it is, the higher the index of refraction. Next problem. A ray of visible light in air is incident on an unknown plastic at an angle of 25.0 degrees. Find the speed of light in the unknown plastic if the angle of refraction is 16.5 degrees. So again, we're given the angle of refraction. It's in air and it's incident on the plastic. So plastic, I'm going to make my right side. By the way, you should always sketch the problem out, just so you can correctly label and identify your angles and which one corresponds with which, and whether it bends towards or away from the normal. Here's my normal. It is incident on an unknown plastic at an angle of 25 degrees. So it hits at an angle of 25 degrees. Find the speed of light in the unknown plastic if the angle of refraction is 16.5 degrees. 16.5 degrees. Oops. Okay, so anything else we need to know? So we're given theta 1, we're given theta 2. Our unknown is V2. We have an equation that relates theta 1, theta 2, v1 and v2, but we need to know the speed of light. We would need to know v1. However, we know what the index of refraction is in air. And air is just equal to 1.00 to 3 sig figs, even to 4 sig figs, 1.000. So, so v in air is the same as the speed of light in vacuum, c, or 3 times 10 to the 8 meters per second. So I'm going to use that equation that relates theta to speed, sine theta 2 over sine theta 1 equals v2 over v1. And since we're solving for v2, all I have to do is multiply both sides by v1 times v1, stop going forward, times v1, cancels here. We get v2 equals v1 times sine theta 2 over sine theta 1. I don't know what's happening. It just keeps going forward. Okay, sine of theta 2, so that's good. Well, let's just write out our numbers. v1 is 3.00 times 10 to the 8 meters per second times sine of theta 2, so that's plastic, sine of 16.5 degrees, divided by sine of 25 degrees, 25.0 degrees. We just plug that into a calculator to get our V2. V2, 3 times 10 to the 8 times sine of 16.5 divided by sine of 25 equals, scientific notation, 2.02 times 10 to the 3 times 10 to the 8 meters per second. And let's just check our work to make sure we're correct. This is a slower speed in plastic than in air, so it should bend towards the normal, and it does bend towards the normal, so our answer makes sense. So here's our summary of refraction. Light changes speed when it enters a new medium, causing it to refract or bend if it hits that medium at an angle. The direction and amount of bending depend on the angle of incidence and the ratio of the wave speeds in the two media. The index of refraction is defined as the speed of light in vacuum over the speed of light in that medium. And Snell's law is the law of refraction, n1 sine theta 1 equals n2 sine theta 2. Hope that was helpful. Bye.